Good morning. My name is Alev. I'm from Istanbul University, and this is my first talk today. Transition parameters for natural silicon. Silicon is an element from periodic table, and you can see that the picture of the silicon, and you can see that here the properties of the silicon is a chemical element with the symbol Si and atomic number 14. It's a member of group 14 in the periodic table. Carbon is above it, and germanium, tin, lead, and fluorine are below it. It's relatively unreactive. So you know that who discovered the silicon and the date you can see here, the year 1823. So in this slide, you can see that the physical properties, it's the solid, and you can see melting point and boiling point and the density for the experimental parts. Yes, it's so important to know that these physical properties and also isotopes of silicon, you can see that these three stable isotopes, yes, these are so important to find that the atomic structure for the stable isotopes. So you can see here another physical properties, melting, boiling points, yes, you can see here, and the other details, yes. Silicon is eighth most common element in the universe by mass, but very rarely occurs as the pure element in the Earth's crush. So you can see that other details information, silicon is a natural element, and when not previously present has a residence time of about 400 years in the world's oceans. So you can see that the periodic table and the group here, yes, 14, it means that the 4A, you can see, and the atomic number 14, you can see that the silicon and the symbol. So we have to understand that the theoretical part of the atomic transition. In experiment, we know that absorption, emission properties of the atom, but in theoretical parts, we have to think about that the selection rules, forbidden lines, and allowed lines. So to find that these results, to understand transition probabilities, and also transition parameters like oscillator strengths, we have to use that atomic programs. This is one of the atomic structure program, HDAC. This is the short name. Yes, in reference, you can find that this program. Also, we have two methods to understand that these properties. MBPT, this, it means that the many-body perturbation theory, and the other one, CIM, it means that the configuration interaction method. So we can think about that transition with these methods, and we can solve the problems. Mostly we can find the atomic programs on relative configurations, relative configurations and relativistic Hamiltonian, and some of them non-relativistic Hamiltonians. But in this program, we can do both of them. Yes, both of them we can use. You can see that the transitions E1, E2, E3, yes, these are multiple transitions, electric dipole and magnetic dipole, and also electric quadrupole, magnetic quadrupole, like this. So with this program, we can solve these transitions and find the parameters. E1 means electric dipole transition occurs only between states of different parities. Yes, it's about the selection rules. M1 magnetic dipole transition occurs only between states of the same parity. And E2 electric quadrupole transition occurs only between states of the same parity. M2 magnetic quadrupole transition occurs only between states of different parities. The next slide, you can see that these energy equation. The first term show that the electric dipole, yes, E1. The second one, magnetic dipole, M1. And the last one shows that electric quadrupole, E2. Yes, this is the simple and the basic, yes, explanations for these multiples. So for the neutral silicium element, we know that 14, the atomic number is 14, so it has for the neutral element, it has the same electron number with the proton number. So you can see here that 226, 22, the total number is 14. This is the electronic configuration of the silicium element. So the next one, you can see how can we use that this program, HTAC. So you can see that the name Hamasha Tahat Atomic Code. This is the authors of surnames of the authors. Yes, you can find that the papers also to understand this program. It is the main way to use this program, you have to know that the atomic number, you have to know that the configurations. Yes, so you can find that the experimental transitions, and then you can understand that the theoretical part, and you can compare, and maybe you can use the relativistic method and the non-relativistic method, and also you can compare these methods. So in this study, we use that. Yes, you can see here. Maybe first I have to say that the initial configuration, for example, the silicon, yes, and also you can see here the final configuration. And for different configurations, we can find the different parameters. And the program gives that these four tables. Alev table means the energy table. Transition table gives that the parameters, oscillator strengths like this, and um, also mixing coefficients, wave function table like this. So in this site, you can see that the result of this program, yes, you can see here, it gives that the oscillators strengths, transition rate, reduce multiple matrix elements. Yes, I will talk this one, these methods, the next talk. Yes, I have to say this one. You know that the upper level and lower level, so the J value, yes, from the fine structure, yes, we know, and we can find that the energy difference, the delta E, this is the energy difference. So you can calculate that the oscillator strengths of these transitions, and you can compare with the NIST. Yes, you can see that the NIST in the reference also. Yes, you can compare that the experimental values and the theoretical values. So maybe I can give a brief about this one. In this study, we calculated the transition parameters, which are transition energies and oscillator strengths. The energies, yes, we use that to compare the experimental energies, but now, yes, with this program, with using this program, we use that the theoretical energies, okay? And the oscillator strengths, theoretical also. Of neutral silicon, Si, yes, Si1, this one shows that neutral, using HTAC atomic physics program. The atomic number of the element silicon is 14. Electron configuration of silicium 1 is given by like this. Yet, yes, you can see here. So these are the closed shell, 1s2 closed shell, 2s2 closed shell, 2p6 closed shell, 3s2 closed shell, but the other one, the last one, 3p2, this is the open shell. So you have to look at this side. Yes, you can see that the tree. We have to think about this shell, the third shell. So we have to understand that these electronic interactions, and we can find that these parameters. The theoretical energy levels of the neutral silicon atom were determined, and transition probabilities between these levels were investigated. The oscillator strengths of 30 spectral transitions in the wavelength, yes, you can see here in the visible light range, you can see 500 nanometer to the 700 nanometer wavelength range was determined. The results were compared with the literature, with the theoretical results and also experimental results. So you can see that the references, yes, in the next title, yes, I will give more information to complete that the transition probabilities for the neutral elements. So thank you very much for your attention. I stop share and see you.